Welcome to episode 20 of the Quantum Science Seminar. Today is all going to be about quantum simulation. And as usual, we do take your questions. So please send us your questions to quantumscienceseminar@gmail.com or use the YouTube live chat at the right or at the bottom of the screen. We're also going to take a break somehow in the middle of the talk to start answering some of the questions as usual, and then we'll answer the rest of your question at the very end. Our speaker today has also very kindly agreed to stay on for a quick chat with all of you after the talk is over, and we will post the Zoom link to that meeting at the end of the talk in the YouTube live chat. Please also note there's a 30-second time delay between what we're doing here and what you're seeing on YouTube. And with this, I'd like to hand over to Andrew, who will introduce our speaker today.
So thanks, Sebastian, and welcome everyone. It's a real pleasure today to introduce someone who really needs no introduction. Through his theoretical work over the past decades, Peter Zoller has originated and pioneered many branches of our field and has also built many bridges between what we do in atomic physics and quantum optics and things that happen in many other subfields of physics. Some of the highlights over the past decades include Peter's pioneering contributions to implementation of quantum gates with trapped ions and with neutral atoms, implementations of quantum repeaters, and the original pioneering contributions to looking at many-body physics with cold atoms and optical lattices. Peter's originally from Innsbruck in Austria and has worked various places around the world over the years, including time at the University of Southern California, the University of Waikato in New Zealand, and he was a professor at the University of Colorado and a Giller Fellow before in 1994 returning to Innsbruck as a full professor, where he's been since then. Since 2005, he's also been scientific director at the Institute for Quantum Optics and Quantum Information of the Austrian Academy of Sciences. For his work, Peter has received very many awards and too many to list, including highlights such as the BBVA Foundation of Frontiers of Knowledge Award back in 2008, and the Wolf Prize for Physics in 2013. The international reach of Peter's achievements are also clear from his membership of 6 different National Academies of Sciences. Peter, it's a great pleasure and privilege to have you at the Quantum Science Seminar today, and we're really looking forward to your talk.
Okay, so let me say thank you for the invitation. First of all, actually, Sebastian, and also Andrew for the kind introduction. So I decided to speak here, announcing a very general title. It's called Programmable Quantum Simulators with Atoms and Ions. But actually my talk here today, I will be a little bit more specific at the end. And you can see that on the left lower side, I've sort of mentioned what this talk really will be about. I would like to talk something that I consider to be one of the fundamental questions that we have in quantum simulation. The reason why we do quantum simulation, what we should actually measure, characterize, quantify, is entanglement. And so the question is, and if you look at the right-hand side over here, can we construct something like an entanglometer, I guess you might call it. If you think about some quantum gas, you might stick in a thermometer and measure temperature and all of these things. But what about entanglement? So we have to develop protocols. And over the last few years, in my group here, we have developed something that we call the randomized measurement toolbox. This has many different aspects. And I think one of the most important one is really how to measure entanglement. And I would like to give you a little review about these things, but at the same time, also, I would like to tell you about the most recent stuff that we did in this context. And we just put a paper on the archive. And at the very end, I'll talk briefly about these things. Okay, so the topic is really measuring, characterizing, and quantifying entanglement in quantum simulation. And I think what I should do at the very beginning is show slides to you that all of you have seen 100 times, in different contexts, because every quantum simulation talk basically starts like this. But it's sort of saying, well, what's the feature of quantum many-body physics or quantum many-body systems? It is the fact that you have entanglement. And what we mean by entanglement is that while in classical physics, the system is sort of cycling, through all of the different configurations when we write down our ensembles. Quantum mechanically, of course, we got the superposition state. We got an entangled state in a multi-particle system. And of course, the feature in this whole story is also the fact that we live in an exponentially large Hilbert space. And so the story of quantum simulation, or then of these quantum devices, then very often sort of starts out by Feynman telling us quite some time ago that, well, first of all, this is difficult to represent on the classical computer, but then also coming up, with a proposal that we should build quantum simulators or quantum computers and so on, where the physical device itself would represent the entanglement. So today, of course, we are at the time, where we build quantum simulators in the lab, and all of you are probably very familiar with what we do. We talk about trapped ions in quantum computing, quantum simulation, and we'll see some experimental results. And later on, optical lattices, Rydberg arrays, polar molecules, cavity QED, photonics, and of course, our friends from the superconducting communities. They are beautiful experiments with, say, superconducting qubits and so on. And I would say that the field has quite advanced, and I think it's sort of time, and people have done this, of course, before, to go back to the roots and remember why we are doing all of these things, and sort of ask the question here: how do we measure, characterize, and quantify entanglement, in particular in light of all of the progress that has been made with quantum simulators during the recent years? So one of these advances that we had is, of course, programmable quantum simulators. And I will give you at the very beginning of my talk a very short overview. I realized that Misha Lukin gave an earlier talk about programmable quantum simulators, talking about Rydberg atoms, Twice arrays, and all of these things. So many people have talked about, various different platforms that apply in this context. So my overview here will actually be rather short. So I will start out with an overview, atomic platforms, and point out opportunities, but then move on to this, what I call randomized measurement toolbox. These are protocols that you can apply to a post-processing in experiments after first, applying certain quantum operations to your quantum state that allow to extract via these protocols certain quantities like entanglement entropies. This was sort of for us the historical first example. And the reason for picking that is that Rainer Blatt was able to do an experiment in his group here in Innsbruck that actually, applied this protocol, and was one of the first measurements of Renyi entanglement entropies. And this could be done in a quantum simulator going up to about 20 particles, and was published over here. But I would like also today to tell you a little bit about the most recent things that we've been doing, and we just put a paper on the archive. And this is called Tomography of the Entanglement Hamiltonian. I think it's opening a new perspective, what we might be able to do in the future. And I will be rather qualitative in talking about these things, but I would like to get across what the main messages are and where I personally at least see quantum simulation going in this context here. So this is sort of an outline of my tour, and let me start now out by those things that are important, namely introducing the people that worked on that. Andreas Elben finished his PhD this spring. He's together with Benoit Vermersch, one of the key people behind the development of this randomized measurement toolbox. Christian Cockerill and Rick van Bijnen, they were heavily involved in programming quantum simulators in a Nature paper we wrote last year, and I will also mention that very briefly. And of course, many of these discussions go back, and I want to give special mention here to actually Marcello Dal Monte, who moved to as a professor to the ICTP now 2 years ago, and has been very successful. So many of these things I talk about here today sort of started as early discussions with Marcello in this context. So having said that, let me sort of jump right away into the first part that I said before will be actually very short, because most of you probably know a lot of these things, and so I can just focus on the essential parts. What do we mean by programmable analog quantum simulators? I guess, well, most of you know what an analog quantum simulator is. We go to the lab, we have our, say, atoms, and on the left-hand side, you can see, of course, this now a very famous example of building what we call a Rydberg Twice array. You take laser light, just a tweezer, you are able to store atoms inside. you are able to see if there's an atom, yes or no there, and you can rearrange this whole thing, producing essentially low entropy, completely filled lattices, where these individual atoms that you have over here, typically they have a distance of about, say, 10 micrometers, say some order of magnitude, represent the spins of some spin model. You know, this is the quantum simulator you would like to build, and then the question is how to turn on interactions between them. And quite some time ago, you know, about close to 20 years ago, I visited actually NIST, you know, talked to several people in Gaithersburg, and one of them was a Rydberg experiment, had nothing to do with quantum simulation, of course, at that time, but sort of the idea came to use Rydberg excitations to engineer interactions between these different spins. And together with Misha Lukin at the end, we started writing papers along these lines. And today we have this great situation in the lab that many of these experimental groups that are listed over here build engineered spin models and hamiltonians. So essentially what they do there is this, that you can realize in the systems hamiltonians like the one indicated over here. You got some laser drive that takes electrons from the ground to the Rydberg state, some detuning, and these ends over here are just the projection operators on sort of the upper state of the qubit. And we have van der Waals interaction. So basically the message is, yes, we know how to build engineered spin models in the lab. There's a very similar story if you go over to the trapped ions. Maybe most of you know trapped ions more in the context of quantum computing. But you can also do a quantum simulator. If you do quantum computing, you have your ions over here in a very long string, for example, with spin up and spin down, representing your spin or your qubit. And then you can shine on lasers to do gate operations. And you can also use the motion, the vibrational motion between these ions here to induce, for example, entangling gates. But if you leave on the lasers continuously, you don't pulse them to do the gate, you can essentially, by eliminating these phonon modes, again, engineer spin models. And there have been great experiments in Innsbruck and also, for example, JQI and so on. So several people in the world are pursuing that. The bottom line of what I've talked about so far is this is analog simulation, in this case over here for spin models. And this is an extremely well-developed subject in the lab. So why do I now call this thing here programmable quantum simulator? Well, the reason is simply that for quite obvious reasons, think of ion-trapped quantum computing, we can add lasers that address individual spins or qubits over here. So we can add not only single site control, but of course we also have single site readout in these devices over here. This gives rise that we not only can engineer these interesting entangling hamiltonians that we have down there, but we have a whole toolbox of operations that we can apply from control, you know, these entangling operations down here, all the way then to the single qubit rotations from this laser or here, or then also the corresponding readouts. And so this is not building a universal quantum computer. This is sort of just building a quantum simulator that has more and more control. And I would say that there's kind of a continuous transition between building a quantum simulator, which, by the way, is really scalable to, you know, system sizes that are far beyond what we can do right now with the quantum computers. Creating a device that's programmable but not universal, but you can do it sort of big scale. And this is quite unique. And I think that that's a fantastic playground, and you can ask yourself what you can actually do with these whole things. You know, the perspective of all of that lies, of course, in the fact that at the moment we are doing maybe 20, well, at the lab actually now 50, I would say. And very soon these things will, you know, go up to numbers, maybe, let me simply say a few hundred, and probably then there's another plateau that we sort of reach, because we're not doing error corrections here or whatever. Maybe at that point, you know, in terms of scaling with decoherence, we might face problems. But having in mind that you can go 100, maybe, you know, maybe larger, is sort of the perspective that we have right now. And now you might ask, what kind of physics should we do with these beautifully engineered quantum devices? And I always like to show from Rainer Platz's lab here this picture of the IQOQI trapped ion quantum simulator that exists now down here with this incarnation of 50 ions, as you can see, that sort of forms the playground of kind of things that one might be able to do. Let me now kind of go back to the roots and ask some basic questions that we would like to do in the context of analog quantum simulation. So imagine that you would like to do a quench experiment. Think of ions here at the moment. You apply your favorite hamiltonian, like this Ising hamiltonian that I showed earlier, you know, propagating these things over a certain amount of time. producing a certain state. Normally what you have is at the beginning you prepare a product state, but of course this quench dynamics that you have over here in quantum simulation gives rise to a state can potentially be a very highly entangled state. And then I'm back to my question, namely asking, can we learn the entanglement properties of these states that we generate over here? Are they highly entangled? What kind of structure do we actually have? Or you can also ask it from the perspective of entanglement as a resource. This is much more sort of, going towards quantum computing, but now with non-universal resources. Of course, what we do in these quantum simulation experiments is that we can read out in a certain measurement basis individually, and you get then, of course, in an individual measurement run, spin up, spin down, getting certain probabilities. And if I call S here the bit string, then we are able to derive here probabilities, for all of these different spin up, spin down configurations, and compute from them quantum expectation values and so on. Let me sort of first, and I will make this very short, make a few comments about this entanglement as a resource. And because this refers to an experiment that Rainer Blatt and also Christian Roos did now 1 year ago, and we published a paper, and we on the theory side were very heavily involved in designing this experiment and even running it, because you have to program these things, and this is what we're able to do in collaboration with the experimentalists. Sort of the basic idea behind this programmable simulator in this particular context is that, well, we have certain basic building blocks of operations. One of them, for example, is this Ising interaction I talked about earlier. This is sort of the standard quantum simulator kind of scenario, but we can intersperse this thing here very naturally with single qubit gates like the one that I indicated over here. So we can entangle this and this, so we can build up, in principle, a very complicated set of wave functions, a whole family, depending on the parameters, how long you leave these interactions on. And this complicated, highly entangled wave function could even be a resource. Of course, this is not universal, as I said before, but one thing is that, well, if I do here in my quantum device certain measurements, I can store them on the classical computer. But then you can think immediately about quantum feedback. And then what comes to your mind is, of course, that this is a very natural setting to do in this non-universal context, but somehow scalable, variational classical quantum algorithms that I guess many of you know so well from the context talking about quantum chemistry and all of these kind of things. One very relevant example is that we can take a cost function, that we want to minimize here, and where this cost function here is optimized on the classical machine. This is the classical computer that we have over here, optimizing these classical parameters that essentially tell you how long you leave these interactions over here on, building up this family of wave functions that I said earlier. And whereas the cost function itself is evaluated on the quantum machine. So you get sort of an quantum advantage by working on the quantum side and being able to do measurements of certain correlation functions that are relevant for the problem. And as I said before, quantum chemistry is a very relevant example for all of that. But also you can do here what we call variational quantum simulation. Maybe there's certain Hamiltonians, your favorite Hamiltonian, your spin system, which has a very complicated structure, single body terms, two body terms, but possibly even 3 or 4 body terms. And if you would like to build such a model directly in your lab, you have no chance. But with the given resources that may be non-universal, as I said, you are able, of course, to write down the expectation value of H, in this wave function. And you can now see that the cost function is now simply a sum of these individual terms of the Hamiltonian that we have over here. And you're able then to measure correlations and then optimize the cost function that you have on your classical computers. This is sort of this typical paradigm of variational quantum simulation of optimizing on the classical computer. So part of the calculations are done quantum and the other one. And we did here, an experiment together with Christian Cockale, who was the first author. He was my student on the theory side. And then the experimental group of Rainer Blatt here, where we built up circuits and so on. It's quite amazingly, we were able to do this for 20 ions with 10 to the 5 cores to these programmable quantum simulators, going to a circuit depth, down here of about 6, and one could increase it. And just to show you typical results, we could do that, as I said, 20 ions, 15 parameters. And then I'm not going to tell you the details about the model. We took a Schwinger model from quantum electrodynamics. you can see very beautifully this convergence down to the value, and which is an approximation for the ground state. And we could monitor all of that. But what was very exciting in this experiment is really that we were also able to measure the error by measuring the variance of the Hamiltonian over here. That gives us the value for the energy, but also the error bar. Okay, if you want to know more details about that, I ask you to maybe either ask me afterwards or then sort of read the original paper, because today my talk, as I said earlier, I really would like to go in somewhat different directions and ask the question, you know, are there other topics where this programmable quantum simulator provides us with a tool to answer interesting physics? And this question of entanglement is the one that I would like to pick up now in this context. And again, these are the people over here that contributed here by really doing the work behind what I'm representing here. Again, same slide as before. Let's talk about quench dynamics, because this is a paradigm that I would like to follow now in the following. So in quench dynamics over here, as I said, we produce a potentially very highly entangled state, and we would like to learn about this quantum state. And we have, you know, these possibilities of these individual readouts here and so on. So what should we do? Okay. Well, what it's done in this so-called randomized measurement paradigm is this, that you take your quantum quenches over here, you produce this wave function, but then you operate on this wave function still in your quantum device, performing an operation, something that at the very, you know, first time you see that sounds completely crazy. You take a random matrix that we apply. This random matrix could be one, which is a global random matrix, which is usually very hard to generate in the lab. But it could also be just individual random matrices that randomize the individual spins by single qubit rotations. And of course, you know, when I afterwards do my measurement and I measure my probabilities, well, the probabilities that I have over here will obviously depend on the way how I randomized, you know, all of these things over here. So U is then a random matrix, and then of course these probabilities are also then random numbers. So you might ask yourself, what have we gained? Well, the basic idea then consists of the fact that we would like to now do measurements of the type where we would like to correlate different probabilities, you know, like correlate probabilities for a given U, where the bit string was S2 that you read out versus the one which was S1 over here. And notice that in writing these correlations over here, we are sort of have two kinds of averages. We have the quantum mechanical averages that go into the probabilities over here. These are the ones that are measured in the quantum device here for a particular realization of the U that we have. But since we are sort of cross-correlating different probabilities over here, this bar that we have up here is really a noise or an ensemble average over these, for example, circular unitary ensemble of these random matrices that you apply. And so it's kind of a hybrid thing that we're doing here. We're doing classical averaging over the U's, and we're doing quantum mechanical averaging over the probabilities that we have here. These experiments, you know, are particularly attractive from an experimental point of view because you only need a single device. You just have to run it more and more often. It's not that you need, for example, 2 copies of a quantum system and then you perform quantum operations on them. This is really that maybe on day 1, you know, in the lab 1, you're doing this kind of an experiment, and maybe on the day 2 in the lab 2, you're doing this experiment. So you know, taking this data may even be sort of, you know, at different points in time and maybe in different labs on the world. And this leads to very interesting possibilities for extracting here from these kind of things, quantities that are normally very hard to measure. But you will see at the very end, there is a price to be paid, because I say here, hybrid classical quantum, it has a classical aspect, this noise averaging here. So when you have a complete quantum protocol, I will usually do better. And I talk about some of these things at the very end. But for the present experimental settings, this is an almost ideal kind of thing to do for these programmable quantum simulators. Well, we've actually written several papers over the last year about these things, very often first on the theory side, like the Renyi entropies and entanglement measurements, cross-platform this year, scrambling OTOCs and Renyi negativities. And actually, you know, based on experimental results here in Innsbruck, you know, many of these theoretical protocols that we developed around this paradigm at the end actually made it into the lab, and we could really see that. And so I'm very excited that this is kind of this randomized measurement paradigm has actually led to a lot of results to measure things that before we thought were sort of very difficult, if not impossible to measure, and we can do them on today's devices. So at this point, it's maybe time to switch over a little bit to physics in the sense of talking about theory behind these things. We want to talk about entanglement properties of quantum states. And I will be very, very simple here, just pointing out some of the important aspects, essentially asking the question, what should we measure when I ask the question, let's measure entanglement? Well, if you got a quantum system over here, and suppose you make a bipartition in the sense is indicated here. You have some region A and the rest you call B, both of them together form the total quantum system. And in quantum simulation, the way that we talk about it right now, we have in mind that what we would like to do is to think about pure states, like isolated systems. Of course, in practice, you always have decoherence. Let's talk about decoherence a little bit later. If I got the wave function over here, it will be a many-body wave function, according to this bipartition that I have here. And I guess all of you in some sense have probably seen that we can rewrite this superposition over here in these regions A and B in terms of what we call a Schmidt decomposition. And this Schmidt decomposition contains all of the information about the entanglement between the part A and the part B. And the question is, how many terms are in this Schmidt decomposition here? We call this lambda alpha here the so-called Schmidt values, and there's chi A in this case over here. If chi A is equal to 1, this whole thing collapses down to just a product state. But if chi A is larger than 0, for example, 2, 3, and so on, and possibly very, very large, then this is sort of a measurement, of the entanglement property. So this becomes, one of the entanglement measures, if you want. All of you that have thought about DMRG and matrix product states, of course, are very familiar with these kind of things. The question that I will ask afterwards, can we actually measure that? And can we measure this thing in quench dynamics here? And to be a little bit more formal over here, we can, of course, define also what we call a reduced density matrix, which is simply taking the trace of this, well, we got the pure state over here over the subsystem B, which is this complement of A over here, defining a reduced density operator. And you can see immediately that this reduced density operator has a spectral decomposition where these Schmidt vectors over here are just the eigenvectors. The rank of this matrix is chi A, and this lambda alpha squares, these Schmidt values, are just the various parts of this reduced density matrix. So if this density matrix is very mixed, it means that you have a lot of entanglement over here, because then the chi A is very large. So at the end, we will ask, can we measure chi A, or sort of the distribution of these lambda alpha squares that we have over here? This will be one of the main focus of my talk then afterwards. Let me rewrite this thing in a different form. The reduced density matrix, of course, being a Hermitian matrix, positive definite, can always be written as e to the minus beta, as e to the minus h tilde. And we call this quantity that we have up here the entanglement Hamiltonian. And you can see the entanglement Hamiltonian is nothing else like the logarithm of this reduced density matrix over here. And we will afterwards ask the question, can we actually measure this entanglement Hamiltonian? Because this contains all of the information that you can ever get about this bipartite somehow decomposition here in the spirit of the Schmidt decomposition we've been talking about over here. This particular entanglement Hamiltonian has eigenvalues, and these eigenvalues, of course, this so-called Schmidt spectrum, as we call it, is simply these lambda alpha squares that we have over here. So you can see that we can sort of summarize what we have heard so far, that we can now define different levels on which we can characterize entanglement. The most simple one would simply be that you would ask yourself, what is the purity of the reduced density matrix, rho A squared, a trace over this thing? Can we measure that? And actually, even at this sort of most simple level, life is not easy, because you can see experimentalists in the lab are able to measure normally expectation values of density matrix that are always linear in rho A. Here we're asking for the square of rho A. So how do we do these things? Randomized measurements provide you one answer for doing that. But then we have higher order Renyi entropies, or the von Neumann entropy. Nobody has come up with a protocol so far. I will show you afterwards how we do measure Neumann entropies from experimental data. Or then sort of the ultimate, I would say, well, can we do a tomography of this entanglement Hamiltonian, and can we learn some physics from that, and also see the entanglement spectrum? How do we measure that? With what physical resources can we do that? So I've sort of given you a kind of a menu over here, where you might ask, why do we want to do all of that? And I found very intriguing this review by Renyi some time ago in Les Souches lecture notes, where he talked about the physics contents in the context of the condensed matter systems, many body systems, why you want to measure, for example, the entanglement spectrum, like detection of topological phases, seeing quantum phase transitions, and I want to say it's one of these examples where if you are a numerical many-body physicist, it's very hard to obtain these things. So I've listed you a few things in sort of increasing order of complexity, and we would like to work now down this list and sort of seeing what we can do in that context. So let me give you the basic idea now of what's actually happening at the end and what kind of protocols we adapt. So randomized measurements. And I want to first review, this was our first example we ever did, and this was also the first demonstration, was this science paper from last year, where we had quench dynamics with a trapped ion system, and we wanted to look at a certain subsystem, asking, for example, the question, can we measure the purity of this density matrix as a measure of entanglement? And the difference to what I showed you earlier is this, that we wanted to restrict ourselves, because that's what the experimentalists can really do in the lab, to random single qubit rotations, or single spin rotations that we have over here. So each of them is a random rotation, but you can see the total rotation that we apply is just a product of single qubit rotations over here. Of course, for each of these UAs, you can work out probabilities and measure them in the lab. And then there was a formula, basically as the structure that I indicated before. We can measure for each of these U's certain probabilities over here, reading out the bit strengths. And if you accumulate all of that, like measuring this probability is, you can cross-correlate them. And there's a formula here that I will not discuss how to derive it, because it's actually complicated. You can see that according to this formula, we are producing a random number over here. And the magic of the whole protocol was that if I take this random number and take the average over many, many unitaries, I have my purity. That's an example of such a protocol where you're running a loop, doing measurements to build up, of course, these probabilities here, but at the same time also running a loop over different realizations of these random unitaries. And if you do these averages, quantum averages, and then here this classical average, you obtain the expression of the quantity that you wanted to have. And indeed, this thing worked in the experiment quite well. This is a quantum simulator here for 10 ions operated in a regime where this sort of effective magnetic field here is actually quite large. Then you just have flip-flops. So your total magnetization is conserved. And if you do quench dynamics, of course, you would expect that if I look in a 10 ion simulator, for example, at the total system, I expect that the whole thing should be in a pure state. And indeed, on the right-hand side over here, you can see some experimental results. This was at the very beginning. This was purity for increasing system sizes. So this is the purity of the total system size. It's supposed to be 1. Well, it's actually a little bit lower over here due to preparation errors, due to measurement errors. This is supposed to be a flat line over here. But you can see that in the course of quench dynamics, the purity sort of goes down, 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 indicating the entanglement. If I plot this thing as an entropy over here, you can see that the entropy is 0, for the individual system, the single spin at the very beginning, but it remains, pure, S equal to 0 for all of the times. But if I do a pi partition over here of my system, you can see that the system is very mixed, indicating that you build up a lot of entanglement. And you can do theory behind these things, of course, by including now decoherence, measurement errors, and all of that. But I will not really continue over here, but simply say that from this experiment, we have a set of experimental data that were taken in this particular context. But I would like to show you now in the following that we can actually use this data now in a way to reanalyze these experiments, extracting things that we never thought about when we wrote this original work. So, it's one of these treasures that Rainer Blatt and Christian Roos gave us by providing us with experimental data that allowed us for many protocols that we developed around randomized measurements to develop stuff, that otherwise you will simply do theory on and then try to convince an experimentalist. But we have now data that we can analyze, from a completely different perspective from this very beautiful experiment here. And that's what I want to talk about in the following. But before I switch over to that, let me go back to one important element, which is randomized tomography. You might ask yourself, well, I computed here, on my device with this protocol, the Renyi entropy, which was the purity, but can we not also get just, the whole density matrix out? If the system is not too large, you might be able to do that. Now, actually, I should make as a comment here, we would like to do these things at the very end, all of these things, in a regime where the subsystem size is really, really large. So we want tomography not to work, to become very, very inefficient. This is really one of the key challenges. But if you want to do tomography, actually the tools that we have also allow you to do that. And here is again a formula that, that the reduced density matrix that we have over here, if you know these probabilities and you sum over these different U's that we have over here, well, you can do, this is another way of doing tomography. Of course, you might ask yourself, how many measurements does it take? How many unitaries does it take? I'll come back to some of these questions a little bit later. And of course, it is very important to ask what is the scaling by the subsystem size. And tomography, of course, has the fundamental problem that it's always exponential in the subsystem size, and you would like to be much more efficient. So in principle, at this point, you would tell me, well, I can go home because I got my density matrix over here. But to tell you, in the experiments for increasing system sizes, and we can do subsystem sizes of 7, then afterwards for this entanglement Hamiltonian, tomography will simply be inefficient. So we would like to do much, much better than what you see over here. But I also want to point out that these ideas are very much related to this very beautiful paper recently written. John Breskill, Richard Küng, and Huang wrote a paper. I really envy them for this name, predicting many properties of a quantum system with very few measurements. I think that this is just, giving meaning to what we want to do. We would like not to use tomography, but sort of try to extract from very few measurements, certain observables. And we will afterwards ask, for example, can we measure, for example, the entanglement Hamiltonian? Can we do a tomography of the entanglement Hamiltonian for achieving that? And that's the topic that I would like to switch over right now. So I'm coming now to the new stuff. I mean, stuff that we did actually this year, being at home and, being exposed to Corona. Theorists find it much more, efficient to work. We don't have to go to travel to all of these different conferences. So we are so bored that we actually got some work done. And the work done was done by Christian and Rick, mainly over here. Andreas was involved and also Benoit in these things, but most of the numerics that I will show you now and the comparison with the experiment was really a collaboration between Christian and Rick over here. So what do we want? We want to ask in quantum simulation what I consider to be the ultimate question. And this is, can we measure the entanglement Hamiltonian, or in other words, can we do a tomography of the reduced density matrix over here, extracting at the end this entanglement spectrum that has so much information about the entanglement structure of the wave functions that we generate in quantum simulation, that this is sort of like the ultimate thing that we can actually ask for. If you're able to do that, I mentioned before, we're able to extract a lot of interesting experimental things like in topological phases. There's the so-called Lee-Haldane conjecture, where the entanglement spectrum is related to the spectrum of the edge states in topology and so on. I mean, there's a long list of things, and we're sort of providing now the tools how we can approach this. I would almost call it a new generation of questions that we can try to answer with the present devices that we have in the lab. So why is this measurement of the entanglement spectrum, or sort of knowing the entanglement Hamiltonian, so hard? Well, I told you before, we could simply say, well, let's do tomography. If I got tomography, I got everything. But all of us know tomography is exponentially inefficient in the system size. And so when I would like to go to, domains where the subsystem size increases, beyond a few qubits, I can certainly not do these things anymore. But that's exactly the regime, which is very interesting. At the end, you would like to be in some sort of a quantum supremacy regime where we cannot no longer do these simulations. I comment about some of these things then also a little bit later. So tomography is exponentially inefficient, but normally when you do tomography, you learn, of course, in quantum information that if you make assumptions about the quantum state, you know something, then of course you can be much more efficient, like MPS tomography or low rank tomography are examples, and there's many other ones. So the question to ask is here, we're doing quantum simulation. Do we know something about the entanglement Hamiltonian up here? And at that point, you will tell me, well, we had an original Hamiltonian, generated a state, took the trace, and I'm taking the logarithm. I must be kidding to tell you that we know something about this entanglement Hamiltonian, or therefore the corresponding spectrum up here. Amazingly, this is not the case. And so let me formulate the challenge. Can we do an efficient tomography of H tilde that gives us the entanglement spectrum? In other words, what is the operator structure of H tilde? How complicated is this H tilde? Is this a random matrix, that fills the whole Hilbert space, or does it have a very simple structure? A very simple structure, like we know from normal Hamiltonians, they just have a few, maybe two-body interactions, single spin interactions, and so on. So what's the structure of H tilde? And what we will now do in the following, that I would like to convince you or persuade you, but at the end show to you, that we can make an ansatz for this H tilde up here, which is quasi-local and two-body terms. I will show this on the next slide and explain it. So we make an ansatz, and I can motivate the ansatz for you at the end at different levels, but one of them will be that we can make it and confirm in the experiment that it's true or not. We can fit this to the data and verify with few measurements. That's a key point over here, few measurements. And so we would like to do an efficient tomography, and you cannot do this for any quantum state. You need quantum simulation where underlying the states that you generate is some simple many-body Hamiltonian. So this is not like quantum computing. This is really that we have underlying Hamiltonians that are physical Hamiltonians. So let me elaborate on this point, because this is sort of a key point over here. We have here our Hamiltonian typical example, like for the iTrap simulator. What do we have here? Well, we have a transverse easing model, with long-range interactions and a transverse field. Look here, there's just a two-body term. There's here, how many parameters do we have? Well, there's really one J naught over here, and there's one B. So the ratio of this just gives you a single parameter. Whole physics, of entanglement is determined by just, very, very few parameters. And the amazing thing of physics is that Hamiltonians that have very simple structure, just two-body interactions, for example, single spin terms, they can generate all of these complicated entanglement. Well, the statement is now, what about the structure of H tilde, the entanglement Hamiltonian? You might say it's probably very complicated, but let me give you an example, and one simple example where you know the answer even, because you heard a course on quantum statistical mechanics. But you know that if I take a system, an isolated system, and I'm doing a quench, this thing, if it's not integrable, will thermalize. And we know that any sub-ensemble that we pick out has the form of a Gibbs ensemble. Well, we can see what the Gibbs ensemble here is just e to the minus beta, the inverse temperature. HA is my Hamiltonian. So just the normal physics Hamiltonian projected into the subset, A that we have over here, our region A, is the one that determines the entanglement Hamiltonian. Clearly here, the entanglement Hamiltonian is quasi-local and looks like a physical Hamiltonian, has actually very, very few terms. But if it depends on few terms, we can actually, find this very, very efficiently. There's more sophisticated reasons, and this sounds now very highbrow, and actually there is. We have the Bisoniano-Wichmann theorem of quantum field theory that tells you that, again, for ground states, there's very specific predictions for this Hamiltonian, all of them having the feature that they are sort of like normal Hamiltonians. They are quasi-local and contain only few body terms, and very similar from conformal field theory. So you can see that at this point, we are trying to make a relation now to these very high-level theory predictions that we believe to be very fundamental, even though most of these things are done in the continuum and not on the lattice. But you might also simply take the attitude, well, let me try it out and see if it works. A heuristic approach and sort of try it out, test it and verify. If it fails, it will tell me. If I succeed, I can write my paper and sort of characterize the corresponding quantum state. So in the following, what we will do is this, that we will make an informed guess about this entanglement Hamiltonian to produce our efficient tomography and add certain corrections to them in new physics. So how do we do that? Well, here's again my Hamiltonian that I just wrote down. So what kind of an ansatz would you write down for the entanglement Hamiltonian? The entanglement Hamiltonian might have, well, you just copy your system Hamiltonian down here, but what was J and B, the physical parameters, and you now introduce as variational parameters. So this is is just a deformation that you have over here of your system Hamiltonian, but you might add additional terms over here, okay? So at this point, this is sort of a typical ansatz that you might make. And what you do then? Well, I told you before, randomized measurements give you a set of bit strings that are indicated over here. We can simply fit the ansatz, fitting these very few variational parameters that we have in our ansatz to experimental data and get the best fit, okay? Let me show now what the outcome is if you apply these things to quench dynamics on this data that I showed you earlier. This is the entanglement spectrum, but now, first of all, here done on the theory side, but I'll show you now in half a minute the experimental data corresponding to that. Then we do a quench dynamics where you start at time t equal to 0, propagating all the way out here doing the quench. And what you can see here is this entanglement spectrum, the buildup of the complicated entangled state, which eventually goes to a thermal equilibrium sort of life. At the beginning, there's just one Schmidt value, which is 1, all of the other ones 0. That's a product state. But now you can see that as soon as we switch on the quench over here, the entanglement starts to increase, and see how many values of lambda appear over here while we propagate towards this thermalization. So you can see here, this is a theory prediction. This red band over here is a simulation prediction of that our measurement scheme should work. And now we can put experimental data on top of these things, very clearly confirming, I think, that this is sort of, for the system sizes that we talk about here, it's a subsystem 5 out of 10 ions. And I should also mention that we can do 20 ions as subsystems of 7, the entanglement spectrum. So it's the first measurement of an entanglement spectrum of this size from old existing experimental data, but we can even do better by constructing from the knowledge that we have now over here, things like the von Neumann entropy. And you can see here, theoretical simulation, that's a black line, how the Neumann entropy will sort of go up and start to thermalize. It goes to its thermalization. And we can extract on different levels of, counting for decoherence or not, our theoretic from the experimental data. And you can see this is the first measurement of a von Neumann entropy extracted from experimental data. There's a lot to say here, about how we deal with decoherence, measurements, imperfections, and so on. I don't want to bother you with all of these details. If you want, you can ask me afterwards. Here is sort of the result for this theory simulation and experimental results for the entanglement spectrum. This is now the xi, here was the e to the minus xi, this was the Schmidt value, this is now the entanglement spectrum here, 4 different times. I think that's quite amazing. I think that we are the first ones that are now able to do that, and the underlying apparatus, of course, is Rainer Platt and Christian Rose's quantum simulator at IQOQI. Similar results exist now for 20 ions in the subsystem of 7. I can show that afterwards. The last thing that we will ask is this: well, you can fit whatever to all of these data and we'll get an answer. How do you know it's right? So testing this ansatz via fidelity estimation is very important. We have written papers that I will not explain to over here, how we can do this fidelity estimation by comparing two density matrix. Basically, the idea is this, that for a given data set, divide it into 2. The first one you use in order to infer, to do the fitting of this, with this efficient tomography, and then you predict, sort of based on that, you're trying to calculate then this overlap with the density matrix from a second data set. And then if you look at this overlap, well, the answer is that I told you before, we just take the entanglement Hamiltonian as a deformation, with open parameters here from our system Hamiltonian. You see that this fit here works well at the beginning, it doesn't really work, but we can add a few more terms to the whole story. And these few more terms, depending, how much you add here, but there are just 3 body terms in this case, we get essentially perfect agreement where we can fit all of these experimental data, for all times. This is quench dynamics. This is highly non-trivial. Get fitting this 5-particle density matrix out here. At this point, you might ask, what do these terms mean? Well, so far I've been using this thing on the level which was purely heuristic, which just make this ansatz, make it more complicated, see what terms are there. That's an opportunity, of course, to discover new physics, but very often in cases, these terms have actually a deeper physical meaning. And I would like to elaborate on these things now a little bit more, speaking essentially about, the Bisignano-Wichmann theorem for quantum field theory, and then conformal field theory, because to be really honest, the kind of things that we want to do at the very end is we would like to build quantum simulators that allow us to address some very fundamental questions like, this Bissoniano-Wichmann theory of quantum field theory that tells us about the entanglement structure, the operator content of entanglement Hamiltonians, and very similar also for conformal field theory. So there's an incredible opportunity here for quantum simulators to make connections to what we consider to be, among the most fundamental predictions that we have in the context of quantum many-body physics on the level of quantum field theory. The following part will be a little bit more sketchy because it's actually a very tough subject, but I want to convince you in the following that it actually works. And but maybe this is also the point here right now where you would like to ask me certain questions, so we can make a break point here because we sort of stopped here at this experimental. It works in a heuristic way, and we are now at the point. Let's try to understand if there's something deeper behind it, more general in some sense, but maybe also more special. Because if I talk about conformal field theories in quench dynamics, it only works in theory if I make a quench to the critical point. And it's in the 1 + 1D system. So these things, these theoretical predictions are very, very limited. They're sort of very small subset. But what we did before, there was no critical point. We just tried it and it actually worked. We could show that we could fit with fidelities, sometimes of 99%, our reduced density matrix with a very, very simple ansatz. Okay, so let me make a break.
So can I interrupt real quick, Peter? So I think we have 5 more minutes for the talk. It depends a bit on how long the rest of your section is.
Well, the rest actually will be pretty fast because I will just go through these things pretty quickly. I just want to give you some basic ideas what one can do, and it's a tough story in principle. But I just want to give you the basic idea. So if you want, I can continue right now. And just
I think that makes the most sense because then I think that makes the most sense because then I think if people are interested, they can join us in Zoom later, and then we can ask any questions they have.
Okay, very good. So there's these 2 fundamental theorems. So in quantum, this Bissoniano-Wichmann theorem, quantum field theory, and conformal field theory. And I would like to give you a very simple illustration of what, for example, the Bissoniano-Wichmann theorem of quantum field theory does. It simply says the following. Suppose they got a physical system like here on the left-hand side, and we assume the system to be infinite, and of course living in the continuum, and you have a certain Hamiltonian density describing this thing. If my theory has Lorentz invariance, then there's a theorem, and the theorem simply tells you that my reduced density matrix has a very particular structure. Simply it says the entanglement Hamiltonian that you can read up here is the original Hamiltonian that has to be local, so we get it, but just multiplied by some effective local temperature. How do we understand this effective local temperature? If you move to a point very, very close to the point where we make this cut, where we sort of define the half space, this is the subpart, A that we have over here. The prediction of this theorem is simply that this beta of x that we have over here is just proportional to the x. So in other words, the entanglement Hamiltonian is just the system Hamiltonian multiplied by x. So just a ramp multiplying in space the system Hamiltonian. It simply means I take a lattice model, and my lattice model, I just take the hopping from side to side, increasing when I'm going here over to the right. This is what this theorem tells. So actually, the structure of this Hamiltonian is predicted to be very simple. I mean, it's not obvious that this thing is true because it works for lattice models. This is not entirely obvious at all for the continuum, but there's been a lot of theory. In particular, Marcello Dal Monte was the person behind that, that came up originally with this Bissoniano-Wichmann in this context, and did a lot of numerical testing and understanding to what extent this whole thing works on the lattice. What we want to ask is, can we measure that? So what we do now is this, that we do theory again. We take a certain Hamiltonian over here, again, our spin Hamiltonian, and we would like to go now to the regime. There's no experimental data for these things yet. We have prepared a ground state, and this has a quantum phase transition from some antiferromagnetic phase to a paramagnetic phase over here. And this entanglement spectrum is degenerate on one side, on the other. Our simulations reveal that we can indeed see all of these things from our ansatzes that we can make quasi-local ansatz. And indeed, if you do this kind of a fitting, you can see that this ramp that I talked about, you know, you can see this linear slope. This is what Biciniano-Wichmann tells you. So if somebody does this experiment I talk about here, you have the first test of a Biciniano-Wichmann theorem in the context you know, of lattice models. Another comment I want to make here is this whole thing efficient? How many measurements does it take? Well, here's the number of measurements versus the subsystem size. Our efficient Hamiltonian tomography is down here. You need very, very few measurements. If you take tomography, the standard way, even something like a rank 2 tomography here, or projected least squares, you know, the number of measurements shoots up here in an incredible way. Whereas in our case over here, we essentially stay flat. So our tomography reveals the main part of what we want to do and is efficient. This is experiment 1. Statement number 2 is this: can we see some new physics in, for example, quench dynamics? Well, let me take the same model that I had before. Conformal field theory sort of tells you the following. If I look at quench dynamics and I look at the entropy growth over here, this is my entropy von Neumann entropy, and we sort of go up here in the linear ramp. If you do the fitting with the local Hamiltonians that I said before, you get this curve over here in our simulated measurements. But conformal field theory predicts that in addition to these deformed Hamiltonian, there's additional terms. We can test for these additional terms that conformal field theory predicts in quench dynamics, in quantum simulation. And if you do that, and if you include these things, we can measure the existence of these additional terms. And this is now the blue curve down here. And again, we can look at cross fidelities. So the simple message is that we have the tools to address some, I guess, of the most fundamental connections that we can make with quantum field theory and predictions and this many-body physics along the lines that I indicated. With this, I'm sort of at the end of my talk, and let me summarize here what we have done and what we want to do. Revealing and quantifying entanglement is a key challenge in quantum simulation. So we have to develop tools for doing that. And what I did here today was to tell you about the randomized measurement toolbox. We talked about protocols from the simple, like entanglement entropies, you know, to entanglement Hamiltonian tomography, which is rather sophisticated at the end, you know, with these local ansatses and all of these things. But I'm really very proud of the fact that, you know, if you apply these things to experimental data, and this is finally, I have to show you the 20 ion, you know, subsystem of 7 datas. This is quench dynamics. Here you can see the evolution of the Schmidt spectrum, the buildup of the entangled state in a quantitative way. You can see these things live here, you know. These kind of protocols are tailored to today's quantum simulation platform. What I showed in this talk was sort of this randomized protocol, which is really classical post-processing on this data that I generated, you know, with these random unitaries over here, and then classically cross-correlating that allowed us to do all of these things, you know. But I guess many of you might ask at this point, you know, can we do something which is more efficient than this sort of half classical, half quantum? Can we even move maybe to a regime where our subsystems we want to talk about are so large that we are in some sort of quantum supremacy regime? Because, you know, at the moment, what we do with our simulations is that we can store all of the data for this reduced density matrix of subsystem size 7 like over here on our classical computers. If you want to go to larger systems, at one point, you might no longer be able to do that. You have to change the protocols from quantum classical to something which is more and more quantum. So the future will be quantum protocols in light of this development of quantum simulators. And we have ideas to go towards no sort of full-blown quantum algorithms for doing that. Bhuvanesh has been working on that in relation to some of the people also here. And we also have ideas how to insert here quantum circuits and couple these things to small-scale quantum computers. So we might sort of in the future progress here from the left, which is this randomized sort of protocols with classical post-processing, becoming more and more quantum, but at the same time learning more about the underlying, you know, about the entanglement that underlies quantum simulation, and of course the synthetic quantum matter that we produce. And here's people involved. Up here is sort of the people directly in this work, and here's the rest of the group. And I also want to acknowledge in particular Marcello Dal Monte's contribution, you know, in starting us off, in particular with Biciniano-Wichmann in a certain direction a few years ago. Thank you very much.
Yes, thank you. Thank you very much, Peter. We have quite a bunch of questions for you here. So we'll start with the first one from Yehuda Band, who is asking if there have been recent advances in characterize the many-body entanglement for non-pure quantum state.
Okay, so I guess that you mean this question in the context of what we are doing here. So maybe let me answer the question over here in a very specific context, which is sort of related to what I talked about here in analyzing this quantum simulation experiment, in the following sense. Ideally, quench dynamics, when theories talk about it, they talk about an isolated quantum system. In reality, of course, when you do an experiment, you always have some amount of decoherence in your system. So a challenge in our case over here is, of course, how in presence of experimental imperfections, and they might include initial preparation, that maybe is a mixed state, but there may be also decoherence during the time evolution, and there may be certain imprecision in the measurements, how we can sort of take out this part over here in the context of our protocol. And the way how we do that is that, well, ideally, our reduced density matrix is simply with an ansatz e to the minus h, and this is our local ansatz. But we can sort of add here decoherence models to this whole thing, where we can try to extract, an entanglement Hamiltonian over here in the presence of decoherence. And this could be done in a way where I would simply include the decoherence in the H tilde over here as part of my ansatz. So my ansatz would contain Hamiltonian coherent dynamics parts, but also a certain amount of dissipation. But we can argue that this dissipation is actually local, keeping the local entanglement, keeping the local structure of this entanglement Hamiltonian, which we talk about over here. And so actually in extracting the data, there's a new fit parameter in addition to the G tilde. And this fit parameter over here accounts for imperfections in the experiments. And we have done some theoretical modeling that this ansatz works really well. And what you can see over here, in this time evolution, extracting the experimental spectrum is actually based on extracting with this kind of a fitting both P, which is this imperfection parameter, and decoherence, and then sort of this coherent part over here. If you don't like this kind of fitting, well, this is the red curve over here. This is sort of the curve that Rainer Blatt would actually plot because raw data, and this is it. If you allow us from the raw data with the model to extract, like what we do over here, the coherent part, you would get this thing down here, which is closer to theory. So you can see the raw data and the other one. And so we understand in the particular context here quite a lot about the decoherence and imperfections and how to sort of extract these things nonetheless in the context of finding the entanglement spectrum.
Great, thank you. We have another question from Bill Phillips. So he's saying that this simulation are done experimentally with systems that they have their own classical imperfection. Could you discuss how we know how well this simulation is being done? We can probably tell that this simulation went wrong by seeing consistency upon repetition, but how we know that they went right?
Let me see, you talk about the classical, okay, maybe let me just start talking and then you tell me if I'm going in the wrong direction. So what you can see over here, so what the experimentalists have done is that they extract bit strings with certain probabilities from these randomized measurements. They have a lot of shot noise, of course, if you want to work out probabilities, all of that. But underlying this thing are imperfections. And the imperfections are, number one, we have a not perfect initial preparation. This system starts out with actually a null state, which is spin up, spin down, spin up, spin down. This will always have a little bit, imperfections in there, in the sense that you can never, get the complete optical pumping locally into a spin up and spin down. This will always be a density matrix. Notice that this kind of imperfection will be independent of the time over which we can do this whole analysis. So this is just initial preparation. Statement number two is this: if you do your final measurements with the random unitaries, it has sort of two parts. You apply local unitaries that can be, for example, have over rotation or under rotation. These local unitaries, for example, can also have crosstalks to the neighboring ions. It turns out that the crosstalk is relatively small, but in the experiment, there was about a 2% error for sort of single qubit rotations that was wrong, okay? actually was found only after the data were taken. And so there's definitely a measurement error that we can model, but both this measurement error that I just talked about, but also the initial preparation are independent of the time over which we do the quench. Statement number 3 is this: that during the quench dynamics that we have over here, there will be coupling to an environment, there will be dephasing. In the case that we have over here, we have spin up and spin down. This is sort of like a kind of a dark state, if you want, regarding fluctuations that you might have in the magnetic field here. So in this sense, it turned out that in this quantum simulation over this whole time periods where this data was taken, actually the decoherence during the time propagation was very, very small. Okay, so we can model that, we can account for that, we can see it, but it is on the level where it doesn't really change. So we even had the plot about these things in the paper that we just submitted. We had the supplementary material, and there's some plot that show the deviation. And so we understand this decoherence very well. So the main sources of imperfections here are really the measurements error and the initial preparation. And both of them can be modeled in the way which is sort of down here with these ansatz. But I'm not sure if I should now go into the details, how we model it. Actually, what we do is a little bit more complicated what's over here. But we are sort of trying to fit, independent of time for all times, this decoherence parameter, because it's related to the initial preparation, it's related to the measurement, which is time independent. Whereas, of course, this entanglement Hamiltonian that we have over here will be time dependent. And, just revealing then, here from the product state and all the way here to the mixed state dynamics that we have over here. Okay, I have a question from Tut Wang. It's asking about variational quantum algorithm. So it's asking, which one do you think can produce results that are really interesting for fundamental physics or from society more broadly? And so they are beyond the toy model. And what's the system property in terms of size, connectivity, depth you need to run these algorithms? Okay, so maybe I should simply start out by sort of reminding you what we did in the case, this paper that we wrote last year with Christian Kochel as the first author, where what we did was that we took a model that's very complicated. It has long-range interaction. You write it down on a piece of paper. Nobody will ever be able to build a quantum simulator. And the question was simply, can with the physical resources that we have available in the lab, can we sort of do a variational quantum simulation of that, and what depths of circuit do we need? Well, the setting there was sort of special in the following sense that there must always be a match between the model that you would like to solve and the physical resources that you have available. For example, the model that we solved then had certain symmetries, and the symmetries were physically realized also in the resource Hamiltonian, which was our transverse Ising model. The other part of the story was that certain symmetries could also be sort of introduced by certain connections between parameters in this quantum simulation, which at the end allowed one to reduce the number of parameters significantly. So I'm simply saying there must be a match between the resource and the problem you're trying to solve. If you simply take your dumb quantum simulator, programmable or whatever, and you just throw it on any problem, you will probably not be successful. So there must be some sort of a happy marriage between the resource that you have in the lab and the kind of problems that you can actually do. This is sort of statement number one. So I'm not claiming that this variational, programmable, the variational quantum simulation with the programmable simulator is sort of the ultimate tool that will provide us for all of the answers. But for many of the quantum simulation problems, probably quantum chemistry in this context is too complicated, it will actually provide a very good answer. And if you ask me, what are other problems that we can solve with that? Changing the world, by variational answers with a programmable quantum simulator, I would be a little bit hesitant. I know a lot of problems where we can try these things, but at the moment I see the forefront of what we're doing here much more along the lines that we can make by, for example, making relation or to conformal field theory or Pisiniano-Wichmann. These are very fundamental questions that we have in physics, and I see sort of a door half open, that we can actually make these new connections and give much deeper meaning to that. So I know that this is not a present that you can give to your grandmother for Christmas, to such a simulator. but I think it may be a very useful tool for us scientists to explore completely new fundamental science.
Thank you very much. I think we stop here with the question. We leave the other for the live session later, and I give the stage to Sebastian.
Yeah, thank you also from my side, Peter. It was a very, very interesting talk, very cool stuff. I would like to finish out by reminding you of our very first Young Researchers session on November 5th, where we will have 3 short talks by you guys. And I'd like to thank everybody for submitting so many exciting proposals for talks. We'll have a careful look and let you know the results by next Thursday. But since we had so many exciting submissions, we are thinking about doing yet another session later this year to give you more of you the chance to present your work. Next week on October 15th, we will have Tilman Pfau, who will speak about quantum gases. And if you want to get notified about what we do, please go to our website, quantumscienceseminar.com, subscribe to our email list, our Google Calendar, follow us on Twitter. Also, you should certainly check out our sister seminar, the AMO seminar, where tomorrow they will have Liang Jiang talking about quantum information processing with superconducting circuits. And if you want to join us for the Q&A session with Peter, please dial in with the Zoom link that I'm going to put into the YouTube chat right now. And thank you for your interest, and we hope to see you again next time. Same time, same place. See you.